Problem 3, longest substring without repeating characters. We are given a string S, and we have to find the length of the longest substring without duplicate characters. So longest substring without duplicate characters. Let's say we have a string like this, and we can examine various substrings. Say this is a substring without repeating characters. This would not be a substring without repeating characters. But let's say this is a substring without repeating characters. But the longest one we can probably find is this. And its length is 6, so that's the number that we have to return. Okay. So I'll try to give you now a kind of probably longer discussion of this problem, which is longer than you would probably need to write it during the interview. But all of these ideas, at least to me, seem important enough to be able to discuss these ideas if there are questions around them. So first of all, let's start with a small warning about time complexity. So a naive solution could be very inefficient in terms of complexity, because imagine if we were to go through every potential substring, right, from left to right. So if we go through every potential substring, that's already O n squared, order of magnitude of n squared roughly, right, where n is the length of the array, length of the string. Now, for each substring, we might need to go through that substring and try to identify whether it has duplicate characters. Now, that's another order of magnitude of n, right? So, and in total, we might easily end up with O(n) cube solution. Now, we can kind of guess that we can do better than that. And the guess comes from an intuition that, let's say we've examined a substring, we looked at a substring and we found that a character repeats. So there is no need to examine any other substring that contains our invalid substring as its part, right? So we could somehow skip all of those. We could skip a lot of substrings that contain the substring that we just discarded, right? So that idea could give us an intuition kind of direction to think. So I would propose the following. So basically what we need to do is somehow go through the substrings while we would skip a lot of substrings that we are sure we won't need, that would not qualify for the title of the longest substring without repeating characters. But while we skip those substrings, we definitely should not skip the one that we need, right? That longest one. There could be multiple longest substrings with the same length, but either one. I mean, we shouldn't skip those. Okay, here is a strategy or an algorithm that I propose we try. So imagine we have just looked at a substring, okay? Now, where should we go from there? We've looked at it, we've established whether it contains duplicates or not contains duplicates. So where should we go from this substring? Which should be the next substring that we'll look at? And I'm going to suggest that we consider two separate cases, right? So we've just examined the substring and we've decided whether it contains duplicates or not. Consider case 1 where it does not contain duplicates. So it's okay. This substring is fine. Now, if it's okay, then it might make sense for us to try to expand this substring and try if a longer substring could work. And we could try to expand it in this direction. Let's say we kind of intuitively, we're going to start from a very small substring, maybe this, or an empty substring, something like that. We're going to start somewhere to the left in the beginning of the string. and then we're going to be moving in this direction, right? So when we find that a particular substring is fine, it does not have repeating characters, which, I mean, ignore this repeating characters here. I'm just talking hypothetically, right? So this substring is fine. We will try to expand it one character to the right, and then maybe another character to the right until it is still okay, until it still does not contain repeating characters. At some point, we may end up in case 2 when we find a repeating character, right? So for example, we find that this character repeats. Again, just humor me hypothetically. Let's say this character we identified just repeated. So now there is no reason, no point in trying to expand the string any further. So we should probably start removing some characters. And we should remove characters from the left, right? Removing characters from the right makes no sense because we just added them. So why don't we try to remove characters from the left? Okay? And you could remove characters one by one, right? In a loop, you could just remove this one character and then try to remove this other character. We may be able to optimize that a bit, but that is going to be the main idea. So basically, this is the main idea, right? So we start somewhere in the beginning with a small substring, let's say. So left and right both point here at the character with index 0. Then we follow this rule when if we know that the substring is okay so far, so it has all unique characters, we just expand, increment the right boundary. Maybe I should use a right green color for this. So we increment the right boundary. Otherwise, if that substring is not okay, if it contains duplicates, then we could increment the left boundary. Yeah. And we'll probably optimize this a little bit, but that is the idea, that this is the main idea, which after optimization, the idea won't change. But we probably need to provide a proof to convince ourselves that this would work. This would finally produce the desired outcome, right? The desired answer. Now, I didn't say when we're going to stop with this, right? So we're not going to stop until the right boundary is somewhere within the string. So basically, until it goes over the string, we're not going to stop. And then while the right boundary is here, we're going to keep moving the left boundary until it kind of makes sense. I mean, you'll see, I think we'll be satisfied with that. So we're not going to stop until the right boundary drops off. And that will be basically the point when we're going to finish the algorithm, right? Now, what remains is to convince ourselves that this will actually work, okay? Right, so let's start thinking about that bit. So this will work if the following happens. If I can convince you that, let's say this is the longest substring, yeah? If I can convince you that at some point with this algorithm, I will be examining this particular substring, okay, then this algorithm will work, right? So I haven't really given you the details. Obviously, you'll have some sort of max length variable, right, which we're probably going to initialize to 0. And then every time we find an okay substring without repeating characters, we will reevaluate max length, right? We're going to potentially overwrite it if we've just come across a better, longer substring, right? So with that, basically, if at some point we're going to end up examining the longest substring with unique characters, then we would be convinced that this algorithm will definitely produce the right answer. Now let's try to prove that. So let's say this right here, this one, this substring is the longest required substring. How do I prove that at some point left and right will be pointing exactly like that at the beginning and the end of this particular substring if we follow these rules? Now, first of all, you should probably notice that if we follow these rules, so left and right will always be, left will be less than or equal to right. Okay? And it's easy to see why. I mean, initially that works because left and right are going to both be 0. So that works. You can see that I'm trying to use induction, mathematical induction, to prove that this condition will always hold. So, but if this holds for a specific step within our algorithm, then for the next step, we're either going to increase R, which only going to make our inequality stronger. So that's good. Or we're going to increase left boundary. And that's potentially when this there is a danger of this inequality breaking down. But think about this. When are we going to increase left boundary? We're going to increase left boundary when that condition does not hold, in the sense that our string contains some duplicate characters. So it has at least 2 characters. It must have at least 2 characters, right? If it has at least 2 characters, then left and right should be strictly less than right. Right? That's just obvious. But if left is strictly less than right, after we increment left, it will remain less or equal to right. So I think we've convinced ourselves that this inequality, this right here, this inequality left is less than or equal to right, this will always hold if we follow this algorithm. I mean, this is kind of obvious, but still requires a formal proof. I mean, that's, say I, for example, wouldn't be comfortable without a formal proof. At least once in a similar algorithm, you have to convince yourself that this type of algorithm kind of produces this sliding window that does not suddenly invert itself, and you get, beginning is far beyond, so it finishes far before than it starts, right? Okay. So this is, let's say, our lemma, that we convinced ourselves that L is always less than or equal to R. Now, we still have, excuse me, kind of almost long way to go to convince ourselves that this longest unique substring with unique characters will actually be examined at some point. Now, I'm going to claim that when left and right, at some point they have, so right boundary has to at some point enter the substring. And it will, because I said I'm not gonna finish this algorithm until right boundary goes through entire string. So at some point, R is bound to go inside this substring here. And when it eventually comes into it, left boundary, let's say, can be somewhere, it cannot be anywhere after the first letter, right? It's not possible. So they could end up together here in the case when, for example, that longest substring starts from the beginning of the string. Yeah. So they could be in the same place, but left can never be after the right. That's not possible. We just proved it inside the lemma. So when right comes in, left is already maximum at the first character, but it could also be still outside of the substring. Now, I'm going to make another claim that, well, right will not leave the substring until left comes into the substring. And that's easy to see because let's say right is about to leave. Yeah, let's get rid of this one. So let's say right is about to leave, but left hasn't come in yet. Now, can we increment R++ if we are following these rules? When are we going to increment right? When the substring is okay, when the substring has all unique characters. But this is the longest substring that has unique characters. Since L is outside of it, this cannot have unique characters, because otherwise that would be the longest substring. It's clearly longer than the one that we've just presupposed to be the longest. So it's impossible that that substring from L to right would have unique characters. Therefore, R++ will not happen. This will keep happening. So I think we've convinced ourselves that. So basically, at some point, R will enter, and at that point, L cannot be past the first character. Now, R cannot leave until L does enter. And the third kind of idea that I want to say is once L does enter, it cannot budge from the first character. It cannot leave this position until R arrives at the end of the substring. Okay? And that's also easy to see. So let's say L entered at some point, and let's say R hasn't yet arrived at the end of the substring. So R is here somewhere. Now I'm going to say that, well, L cannot budge, right? And let's look at it. Can L increment before R arrives at the end of the substring? Now, when do we increment L? We increment L when the string is no longer valid, so it contains some duplicate characters. But this cannot contain duplicate characters because we know that even the entire substring does not contain duplicate characters. So obviously, its subsection cannot contain duplicates. So that means R will be incremented, not L. And because of that, that logic works all the way until right boundary reaches the right edge of that longest substring. So we've proved those three little things plus this our lemma. So together, I think you can see that at some point, we'll be looking at, definitely be looking at the substring. So we'll examine the substring and we'll compare it to the maximum length of any valid substring that we've seen before. So definitely this algorithm should produce the correct answer. Now here is one kind of important bit here. How are we going to ensure? So every time we need to make a decision whether we should increment R or we should increment L, we need to make sure, we need to kind of decide whether this substring contains duplicates or not. And we could do this in various different ways, some of them more efficient than others, but here is what I would propose to you. So why don't we just try to ensure that this string kind of never contains duplicates? Okay, and how we do that? By quickly moving left boundary, by skipping as many characters very, very quickly as required so that all of the characters are unique. Okay, and to do that, here is an optimization. I mean, this is just an optimization. You will see this does not really change the idea, change the algorithm. So what if I have a map of last index of each character? Last index. Okay. So let's say for each of those characters, you know, A, B, C, and so on until Z, I have an index, which basically an index, which is where this character was last seen. And initially it could be, okay, let's say it's undefined. Initially, all of them are undefined, right? Or we could initialize everything to -1, but let's just keep it undefined. So every time we expand right boundary, so every time we expand right boundary, this is the only time when we're going to find a new character. And when we find a new character, I mean, obviously we could kind of update where the last index was seen, right? So whatever, 17 or something. But before we do that, now imagine that we're going to try that the string is always unique. The string always contains unique characters. So let's say this is preserved. We will preserve this property that this string always contains unique characters. So once we add a new letter, new character, so by adding this character, only this character can be duplicated, and only once, right? Only this character, because we've just added A, everything else was unique. The only thing that can be duplicated is this A. So before we update this last index, we could say, well, have we already encountered this somewhere? Have we seen A? Where was the last that we saw it? Let's say it's undefined. Oh, then that is fine. We don't have to. We can quickly realize that our left index can be left where it was. Yeah, it's fine wherever it was. But if we found that A was already seen, let's say at 5, let's say it was seen at 5. Where? Well, I mean, ignore these actual letters. So let's say A was seen here. That's 5, let's say, index 5. Now, left is over this 5, right? It's strictly more than 5, which means, well, this is not going to be a duplicate. This is not going to be a duplicate because left boundary has already moved beyond this. So, but if this index, the last index of the letter that has just been added, if this is less than or equal to L, right? Then we have to move L past that index. Then we have to move L past this index. So 5 plus 1, right? And then only then we could overwrite this number and say, okay, 17 is now the last index of this letter. Okay? I think we don't need too many proofs here that this will actually not change anything. Basically, what this will do is we will still be following these rules. Simply, the only thing we'll be doing is these L++ will just be doing them just more efficiently. Maybe kind of simulating multiple L++ just with one operation, just by knowing where precisely the left boundary should be moved so that the string remains made up of unique characters. Okay? Now, let's try to write this. Let's try to implement this. Now, I'm not going to try to implement this inside LeetCode's editor. I'm going to copy this function into typescriptlang.org. So typescriptlang.org. Now, what we said was the following. So first of all, we need that last index map, right? So let's say last index, and that would be new map. And that map is what sort of map? So it takes a string and number. So it maps basically characters to a number. So probably a better type would be if you had something like type letter equals A or B, etc. But that's only going to complicate things. So I'm just going to keep it string to number, although the actual type here is a character to number, right? So if you're writing this in another language, that's a different type of situation. Now, what else do I need? So we need here, we said max length, and we're going to turn it into 0. So we're going to initialize max length to 0, which is fine. Let's say we did not find a substring with unique characters, which would be only in the case when S is empty. Then returning 0 would make sense, right? If algorithm did not do anything and we return this max length in the end, why don't we actually do that? So then that would be correct, right? So if nothing here runs for the reason that, let's say, S is empty, then this return is correct. What else do we need? So we need left and right. Okay. So I'm going to define left equals 0 and right equals 0. You know what? This will probably be defined inside the loop. So for why don't I actually move left and right inside the loop as well? So left equals 0, right equals 0. Now, right should be less than S length. Okay. And plus right. So notice that left is just sitting here. Left is neither being incremented in the header of the loop, neither being it is being checked in the exit condition of the loop. So none of this is going to happen. But we will ensure in a different manner that left is always properly updated inside the loop. Okay. So first of all, let's say character equals string and what? Right. This is going to be the current character that we're going to be adding, right? So when we come in, initially right is 0, so character will be S0, which is fine. And every other time we come in, we're going to update right, and character will be initialized within this loop, the body of the loop. Character will be a constant, basically the one character that we've just added by updating right. Okay. Now, so in the end, just so that we don't forget, remember what we have to do in the end. Basically, what we have to do is last index of this character should be set to right. Okay. Oh, sorry. This is not correct. Although I could use an array here, obviously, but let's just keep set. And the character is, where is the character? It's character to right. That's the syntax. Okay. So we're going to set the last index of this character to this position here, right. That's what we have to do in the end. But also before, we need to at some point update max length, and that should be the maximum value of itself. And also right minus left plus 1. Okay? Why? Because when we come here, we will already have moved left, if you remember our optimization. So we're going to try to move left to the point when the string is always unique, made up of unique characters. So this is going to happen here. This is going to happen here. So move left so that substring has unique characters. So if we somehow manage to do that, then these two commands are fine, right? Now we can update last index of this character to this position, and max length can be set. Well, left is now to the position when the string is made up of unique characters. So that would be the current length of the substring with unique characters. And therefore, this is a correct expression to try to update max length. Now, the only thing we need to do here is somehow move left so that substring has unique characters. How do we do that? Well, here is a character. And let's say last index would be what? Last index would be, last index of C. Let's call it last occurrence would be last index get character. So that way, now this could be undefined, exactly. This could be a number or undefined. That's correct. Now, when should we move left? If last occurrence is not undefined, I mean, technically, we don't have to ask that, but for TypeScript, we need to ask this. I mean, it's not just TypeScript, it's a better thing to do. But anyway, I'll make clear what I mean. And last occurrence, if it is less or equal to, last occurrence is less or equal to right, correct? Then right is not valid, yeah? So, no. Last occurrence, if last occurrence is greater or equal to right, yeah? If it's the same, then obviously this is not good. If last occurrence is the same as right or even later, that means our right is not valid. I hope that makes sense, right? So here is, let's say, let's get rid of some of these garbage here. So what is the last occurrence? Last occurrence is where we've last seen this new character. This new character, let's say, was last seen here. So if this last occurrence is after this point, at this point or later, right? So if last occurrence is greater or equal to left, isn't that what we did? Left, sorry. So if last occurrence is greater or equal to left, then we have to move left. So left would be last occurrence plus 1. It needs to be plus 1 because otherwise if we just if we move left to last occurrence, then the substring will contain two duplicates exactly at the beginning and at the end. Okay? So I think that's it. That is the entire thing. Why don't I copy this now back to LeetCode, paste it here, collapse it, and now I am going to try to submit it to the pretests. Let's see what happens. Okay, pretests passed. Let's now submit this to the full suite of tests. And okay, we did pass. It's 94% of solutions in terms of speed and 92% of solutions in terms of memory, which is pretty decent, I think.